Hi, my name is Arlo Jones. I've been working on this project we've titled The Midnight Zone with my friend from back home. His name is Chris. And I just wanted to go through and demonstrate some of the technical aspects of the code and talk a little bit about the design. There's a lot to unpack, but I'll kind of just jump into most of what you'll see on screen. During the game, we have on screen actors, or what we've called them. They're entities that can move around, attack, shoot, etc. Each actor has two major components that are modular. You can swap them out. They have a view, which represents or which contains the sprite, as well as a hitbox and animations and things like that. The other major component that an actor has is a behavior, which is a set of code that determines how the actor will attempt to move and what abilities they will be using. So here we have just a basic enemy. We call it a drifter. Um, it has a little animation and it fires bullets. If we switch over to scripts, you can see kind of how the uh, drifter is specified. We have a JSON file for it specifically that has all of its stats as well as its abilities down here at the bottom. These files of actors are compiled into a wave of enemies, and that's specified here. We have several drifters, what their spawn positions are, and when they will spawn as a delay to when the wave begins. And then several waves are compiled into a level. So you can see that here we have different waves of different enemies all kind of compiled together to create the several levels. The game has four kind of gameplay levels, a fifth level that is meant for just playing with the particle effects, and a sixth level that is meant for kind of customization if you want to make your own. Diving deeper into the code, we can switch over to Visual Studio and I can describe kind of the process by which the actors are instantiated. We have a level manager. So when a level has been selected, that JSON file will be loaded into the level manager. The level manager will go through and extract out of it which enemies need to be spawned in. And it does that down here. The level manager is also responsible for kind of keeping track of time and bringing up waves if they are defeated early so that they aren't done so there's no delay if you defeat a wave waiting for the next one. When it spawns in actors, what it does is it creates this spawn actor command. We're using a command coding structure. So this is what that looks like. This deferred spawn actor command really just tells an actor builder to create the actor, but it's not executed right away. It is instead put onto a queue in this execution manager, and this allows us to kind of queue up a whole bunch of actors to spawn at different times, and also to do other in-game events. This just goes through and checks when, or what the current time is, and if anything is queued up, and it then will execute the command. That command, like I said, tells the actor builder to build the actor from the JSON file that I showed earlier. That's done here. This is actually set up using reflection. So it is able to kind of go through all of the code base and scrape all of the different behaviors, all of the different views, all of the abilities, and then compile those into a single actor as specified by the data in the JSON. And that allows us to add abilities and such without having to recompile the code, which is exciting. We can kind of treat it as a library. And once it has been built here, it is returned and put on screen, which allows you to kind of interact with it. The player itself, the character that you play, is also just an actor like this. It has its own unique behavior. So I can go into one of those behaviors now, so you kind of see what that looks like. Here is the generic behavior that different behaviors inherit from. The primary thing that it does is that it has this get actions function and this get translational force function. Essentially, each frame we are able to ask the actor and therefore its behavior, hey, what actions are you trying to execute right now? And also, how are you going to be moving right now? When it actually comes to moving, go to the definition here. The actor kind of has a composite movement where it uses both its internal get translational force here, but also the forces that are acting on it by physics. And if we go look at what the physics of that looks like, we have this vector field manager that kind of does most of the behind the scenes physics. What we wanted to do was be able to simulate the fluid forces that are acting on the different actors and the bullets in the scene. And so what we wanted was to be able to essentially query saying, here is my position in space, what forces are acting on me currently. And vector fields are a really kind of elegant way to do that. And what's nice about them is that because they're just vectors, because what is returned by the vector fields is just vectors, you're able to add them and get these kind of composite acting forces with different math equations. We also have different channels. So you can have forces that are purely because of the fluid in the world, but we could also add forces that act only on an actor of a given type or something like that. You're able to subscribe to which channels you want to influence you. This is kind of the core logic of it. It goes through all of the fields that are currently active and compiles the force vector from each given a position into one total vector that is then returned as the force that acts on the actor. The vector fields themselves, they're kind of interesting. It's difficult math-wise to modify the equations to account for like moving the origin or rotating. However, it's not difficult to do it relativistically, where we move the actor relative to where it would be on the vector field, and then move it back. And that allows us to get rotation and movement that way. And that's what this get relative position and real vector are. In the different vector fields, they overwrite these generate I and generate J because we're in two dimensions, and that's the crux of the difference in the math. Because of kind of the scaling that vector fields typically have, we also have these adjust length functions that make it so that you're not moving 10,000 pixels a second once you're more than 100 pixels away from the origin. We're able to kind of scale all that down linearly based upon how far away you are and that sort of thing. We also have vector field adjusters that are able to modify the parameters of a given vector field over time. And that allows us to, say, rotate one direction and then rotate the other, or scale the strength of a vector field up and down to kind of give it a smoother feeling. Um, that is all just kind of the math back end of the physics. The issue is how do you communicate that, like how the fluids are moving for the player. And so back in Vector Field Manager, we spawn in these phytoplankton that, where do we have that? We have these uh, that are reminiscent of real life bioluminescent plankton that light up when they're moved or agitated. And that's what ours do. And they will stay active for as long as they are moving. But if they are at rest for a period of time, then they disappear and they head back into the kind of phytoplankton pool, which allows us to kind of keep a cap on the memory here when we're spawning them in. And those phytoplankton are subscribed to the fluid field so that they can kind of show what is happening in the water, and that really helps communicate things to the player. I think that's a pretty good highlight of the majority of the important code. But talking about the gameplay a little bit, uh, we did some things design wise. We have 5 different types of enemies, I would say, that are each meant to challenge the player in a unique way. And each of those types has both a basic form and a more challenging form. So we have enemies that have really high health and they take a while to kill. Enemies that deal a lot of damage, they just spawn a lot of bullets on screen. And that's what this drifter does. We have enemies that are very quick. We have enemies that are antagonistic. They force the player to move mostly through things like homing bullets. And then we also have enemies that are meant to be chaotic and hard to predict, which means you have to be very reactive and quick to deal with them. And then the advanced form of each of those, the basic form is mostly done through the different stats and kind of movement patterns that each one has. The advanced forms also get additional abilities that make them more challenging, that have to deal with the vector fields or additional defensive abilities or things like that. Which you'll see in the gameplay footage. One other thing we did to kind of change things for the player was we made it so that the player JSON that is used to load the player in is different for each of the 4 levels that we have. With the first level, you kind of just have moving and shooting, and there's a dash. And that's about it to kind of help you get acquainted with everything. In the second level, you're given the ability to create kind of a column of water that pushes enemies and bullets away from you, which can be used to, A, defensively to push things away from you, but B, to also kind of accelerate your damage and extend the range of the bullets a little bit as you kind of push a bunch of them at once into an enemy. And then in the third and fourth levels, we add 2 new abilities. I call them Singularity and Whirlpool. One kind of sucks in bullets and enemies as a way to kind of keep them away from you or group them up so you can shoot them quicker. And the other one, the Whirlpool pushes everything away from a central point, which can be very useful if you put it on the player to push things away from you. I think that about highlights the gameplay and the code structures. Please let me know if there's anything else you would like to see. Thanks.